We are still on work, power, energy, and machine. In the morning, we tried to look at some of these terms. We looked at work, for example. We defined work as the transfer of energy using some force to an object and causing the object to move in the direction of action of the force. Remember, we said that force is a vector, and therefore it has to be defined by direction as well as the size. Therefore, if we take the two into consideration, we have a certain amount of force. Again, we agreed that force is measured in newtons. This force is applied on an object, and for there to be work done, the object has to move in the direction of action of the force. Okay, we went ahead and looked at power. Power, again, we defined it as the rate of doing work. Rate of doing work. In other words, we are saying that power is the rate of transfer of energy using a force to an object and moving the object in the direction of action of the force. Therefore, you are rating how fast have you transferred energy, or rather, how fast have you moved the object. Now, the third term, which we are going to dwell on for a long while this afternoon, is energy, and we defined it as the capacity or the ability to do work. Remember, we said we have to have a force which is causing movement in the direction of its action. Therefore, you have the force, and it is working at a certain rate, but is it able to cause the movement we are after? It will require the energy to give it the capacity required to work. Now, let us shift our attention to forms of energy. Forms of energy. Forms of energy, or what we would call the types of energy. We've got quite a number of them, and very first we start with number one, chemical energy. And chemical energy is the energy generated through chemical reaction. Is the energy that is going to be generated through a process of chemical reaction, And basically, it will entail breaking of bonds. Breaking of bonds in elements. Breakage of bonds is actually accompanied by release of energy, and you have to make sure that the energy now thereof is then transferred in order for it to perform some task. You can also have some energy when you form bonds. There are some bonds that whose formation is accompanied by release of some energy. Number 2 is what we call ionization energy. Ionization energy, and it is the energy generated when an atom loses an electron to form an ion. That ionization energy is that energy that you will generate when an atom loses an electron to form an ion. Now, in the course of studying science, you will come across ions formation, and you realize that some atoms of elements will form their ions by gaining electrons, while others will form their ions by losing an electron. Now, in this class, we consider only those ones that lose. Those ones that lose. In the process, energy is generated, and if that energy is put to use, then it will be classified as ionization energy. Now, we look at our third, and our third is what we call elastic energy. And elastic energy is the energy released when an object is deformed. When you distort the shape of an object, some objects will release some energy, and that energy can equally be tapped and put to another use. Number 4 is nuclear energy, and this basically is energy released or generated during nuclear fission or fusion. Now, energy released during nuclear fission or fusion. Now, nuclear fission is the division of a nucleus of an atom of an element, while fusion is the joining of 2 or more nuclei of atoms. When that happens, energy is given out. And if you are interested in that kind of energy, you call it nuclear energy. Now, there is what we call radiant energy, or what we call the radiant energy, and it is energy possessed by electromagnetic radiations. Electromagnetic radiations. And we shall have a whole chapter on the same. We shall try and understand what it is that we refer to as electromagnetic radiations. Now, the last one, or the second from last, is what we call thermal energy. And thermal energy is the energy transferred as heat. Whenever you have energy transformed in form of heat, we call it thermal energy. Number 7 is mechanical energy. And this one comes in two types. One, we call it kinetic energy, and the other one is what we call the potential form of energy. Now, what is the difference between the two? Kinetic energy and in some cases it is called KE, is actually energy possessed by bodies in motion. It is actually energy possessed in motion, and it is given by 1/2 mv², where m is the mass of the object, in question, and v is actually the velocity of the object. Remember, we have said that kinetic energy is only possessed by bodies in motion. Any body has some mass, and if it is in motion, then definitely it will have to be moving at a certain rate, and that is what we call the velocity. Now, let us look at a numeric example involving kinetic energy as a form of energy. A car of mass 1200 kgs moves at an average speed of 20 meters per second. Calculate its kinetic energy. Let us look at that. A car of mass 1,200 kgs moves at an average speed of 20 meters per second. Calculate its kinetic energy, and we go about it as follows. You say that kinetic energy is given by a half mass times velocity squared. Therefore, in our case, we shall have a half mass, which is 200 kgs, and this one we multiply by velocity squared, or other, we can also write it as a half of the mass multiplied by velocity, and you do it twice because it's a square, and this one will give us 480,000 joules. 480,000 joules. Now, how about potential energy? Now, potential energy is also a form of mechanical energy, and we write it sometimes as PE, and this one here is the energy stored by an object at rest in a force field. Remember, we looked at types of forces and we came up with two. One was the contact force, the other one was the non-contact, or what we called the field forces. The field forces, and we gave examples of magnetic field, electric field, electrostatic, field, And the most common, which we call the gravitational field. The gravitational field. Now, any object placed anywhere where the influence of these field forces is felt possesses this form of energy that we are calling potential energy. Now, potential energy, in our case here, we shall consider the potential energy of a body that has been placed in a gravitational field, and we are going to call it gravitational potential energy, and it is given by mass times the height times g, where m is the mass of the object, h is the height of the object, or the height to which the object has been placed, and the g is gravitational acceleration. Is gravitational acceleration. We look at an example involving that, and we say a ball 2 kgs in mass is placed on a hill 7.5 meters above the ground. Calculate its potential energy. Calculate its potential energy. And in this case, note that we are dealing with gravitational potential energy. And to the solution, potential energy, some other books will even call it gravitational potential energy, is given by mass times height times gravitational acceleration. In our case, our mass is 2 kgs, so we multiply it by our height, which is 7.5, and our gravitational acceleration, which is 10 newtons per kg, and this one brings us to 150 joules. That is the amount of energy that ball will possess. Let us look at this pendulum bob it will help us to really come up with an interesting discovery. Yeah. Now let us assume we are swinging the bob. This is the pendulum bob. And we are swinging it from A through B to C. And we are going to follow the trajectory yet again. Now, here, the velocity of the ball is 0. The velocity of the ball is 0, but the height to which it has been raised is the maximum, and we will call it the maximum height. Now, here, the velocity is maximum. Here we have said velocity is 0, but the height is maximum. Again, if this is the ground level, the velocity here is maximum and the height is 0. Again, if we consider it at this point here that we are calling A, again the height is maximum while the velocity is actually 0. Remember, we said that mechanical energy can either be kinetic or potential. Now, at point A, or rather, before we go to point A, I will want us to consider kinetic energy is given by a half mass times velocity squared, while the potential energy is given by mass, height, and gravitational force. Now, at this point A, at point A, velocity is 0, and therefore our equation, a half mv squared, is reduced. To 0. How about potential energy? Potential energy is given by mgh. This is potential energy, which means now that our height is maximum, if we substitute it in our equation, it means that our potential energy will be maximum at point A. Now, the same scenario is going to be repeated at point C. At point C, so let me add A and C. That is our case 1, that at C, V is 0, which means our whole equation of kinetic energy is going to be 0. However, potential energy with our height rising to its maximum is maximized by itself, and therefore potential energy at C and A are maximum. Now, let us look at point B. Now, at point B, this one, velocity V is maximum. Our velocity is maximum. And when we submit it to our equation, now we shall have maximum kinetic energy. How about potential energy? At this point, height reduces to 0. Now, if we go by what our equation says, M, H, and G multiplied together, and now that our H is 0, it reduces the whole equation to 0. Now, let us look at point A and C. If we add, for both cases, kinetic energy plus potential energy, and again we add for point B, we look at kinetic energy plus potential energy. Now, at point A and C, kinetic energy is maximum, while potential energy in itself is 0. While at B, kinetic energy reduces to 0, while potential energy is again at its maximum. Now, that is to tell us, if you increase the potential energy of a system, say at point B, you reduce kinetic energy of the same system. And when you reduce the potential, the kinetic energy rather, the potential energy subsequently reduces. And that brings us to the law of conservation of energy. Law of conservation of energy. Law of conservation of energy, and it states that energy cannot be destroyed or made, but can only be transformed, formed from one form to the other. Can only be transformed from one form to the other. Now, let's take the case of mechanical energy, for example. Mechanical energy entails kinetic energy and potential energy. Now, in terms of the two, how can we express the law of conservation of energy in numeric form? Kinetic energy is given by a half mass times the square of velocity. Potential energy, on the other hand, is given by mass multiplied by height and the gravitational acceleration. Now, our law in terms of the two can be written as kinetic energy plus potential energy will always give a constant. Like we have seen in the case we have just studied of the pendulum bob, you increase kinetic energy, potential energy decreases by an equal measure, and vice versa. Therefore, if you add the two for any given system, it's supposed to give you a constant, and that constant is what we call the mechanical energy. Therefore, at any given point, mechanical energy of a system will always be given by kinetic energy and potential energy summed up together. Now, let us look at an example where we shall use the equation of mechanical energy conservation. Example 1. Now let us look at that question. A person is sitting on a building and the height of the building is given as 10 meters. If his mass is 76 kgs, we are required to get the mechanical energy possessed by that man. But we have said mechanical energy is given by kinetic energy plus potential energy, and our kinetic energy is given by a half mass times the square of velocity, and this other one is given by mass, height, and gravitational acceleration multiplied together. Now, from the question, the mass is 76 kgs. Now, velocity is 0 because we are told he is actually sitting. Height is 10 meters and gravitational acceleration is 10 newtons per kg. Let us now try and come up with the mechanical energy of the man. And the mechanical energy from our equation, we substitute 76 kgs then per times 0 squared. That one you add to 76 multiplied, 76 are actually kgs. We multiply that by 10 meters and then by the gravitational acceleration. Now the whole of this reduces to 0. Now this one becomes 7600. Remember, this is energy, so it's in joules plus 0 joules, and this one will give you 7,600 joules. That is the energy the man will possess by virtue of sitting on the building that we have discussed. Now, let us look at yet another example. Example 2. It requires us to determine the mechanical energy of a 20 kg object moving with a speed of, or at a speed of 20 meters per second. Now, mechanical energy is given by kinetic energy plus potential energy. The question provides mass as 20 kgs, velocity as 20 meters per second, h is 0, and g is 10 newtons per kg. Therefore, the mechanical energy will be given by a half multiplied by 20 kgs by the square of the velocity, and this one we add to the same mass multiplied by height, which is 0 meters, then times gravitational acceleration, which is actually 10 newtons per kg. The whole of this reduces to 0. So what we are left with is actually 8,000 joules. Briefly, let us look at the relationship between mechanical energy and the work done. The relationship between mechanical energy and the work done. Now, work done, remember, for us to claim that work has been done, there has to be some movement of the object on which we are, there has to be a movement of the object on which our force acts. Therefore, if motion has to be involved, then this relationship has to do with kinetic energy only, because objects possess kinetic energy when they are in motion and potential energy when they are at rest. Therefore, if work has to be done, motion must be involved, and therefore kinetic energy is the energy to consider. Now, work done is given by change in kinetic energy. That if there is change in kinetic energy, then work has been done. Let us illustrate that by way of example. By way of example, a car of mass 1000 kgs traveling at 30 meters per second has its speed reduced to 10 meters per second by a constant braking force. Over a distance of 75 meters. Now, question number 1. A car of mass 100 kgs traveling at a speed of 30 meters per second has its speed reduced to 10 meters per second by a constant braking force over a distance of 75 meters. Now, we have 4 parts of that question. Part A requires us to get the initial kinetic energy. B is for us to get the final kinetic energy. We shall also look for the work done, and finally find out how much is the braking force or the initial kinetic energy will be given by a half multiplied by mass multiplied by velocity 1 squared, which will be given by a half times 1000, then we multiply that by the square of 30. Now, we can cancel, and this will give us 45 or 450,000 joules kinetic energy will be given by a half multiplied by mass times V2 squared, which is a half times the mass, which was 1000, times 10 times 10. This gives you 5, which will give us 50,000 joules. Now, work done is initial kinetic energy minus final kinetic energy, which will be given by 450,000 minus 50,000 joules, giving us 400,000 joules. Now, the last part of the question is on the breaking force. That is actually part D of our question. And the breaking force, we shall go about it using work. We say that but work is force times distance. We have our work done as 400,000 joules. We want to equate this to the force that we are looking for, and then the distance through which the car moved before its speed reduced to 10 meters per second. And we can make F the subject by taking 400,000 joules and dividing it by 75 meters, and that will give us 5,333.33 newtons. Remember, this is a force, therefore the units are newtons. Too much about relationship between mechanical energy and work done. Next time we meet, we will talk about sources of energy. Sources of energy. Have a good afternoon. Thank you.